Okay, so up to this point in the course, we've looked at Turing machines, and we've used Turing machines to define language problems and to classify whether they're decidable or semi-decidable, or even maybe neither. So we use it to define decidable and semi-decidable languages. And also in, I think, the first lecture, we use them to define what it means for a function to be computable. So computability of functions. Sorry. Functions from well, because we've got Turing machines, so the idea of the computing a function, so you transform some input data to some output data. The only data you have available is words over an alphabet that you can write onto a string. So the kinds of functions we were defining were functions that transform words over potentially some input alphabet to words over another, well, an alphabet that could potentially be different, although both alphabets need to be part of the take alphabet. And because I haven't put an arrowhead here, and the reason for that is with Turing machines, we've got the fact of life that when you start a Turing machine running, it may terminate in the halt state with a nice output string, and in which case that's fine, you've got a result. But in general, an algorithm isn't guaranteed to terminate. Algorithms may compute forever. And so in general, it's natural, the right level of generality for looking at computing functions is not just computing total functions, but more generally computing partial functions. Total functions are a special case of partial functions. The more general thing is to look at the computability of partial functions. And in this course, we're going to have to be quite careful about distinguishing between partial and total functions. So I'm going to be maybe a bit heavy-handed with the notation, a bit more. I'm going to be more careful with the notation than one normally is in mathematical courses, because partiality is going to be very important. So I'm going to use always this, I think I've already said that I'm going to use this partial arrow here for the space of partial functions, and that's missing space here is because I wanted to emphasize that we're looking at the computability of partial functions. And you remember, hopefully, we had a special kind of Turing machine for computing functions, namely the one that had a halt state that it could halt in. And to compute a partial function, when we gave it an input word, what the Turing machine had to do was, if the input word was in the domain of the partial function, it had to compute and end up in the halt state with the correct output word according to the function on the results plane. Okay, so before carrying on, I just want to make some very simple observations about partial functions we compute. The first one is the identity function is always computable. That's a total function. So that takes an input word and maps it to itself. So that is from an alphabet. It's a total function. Given a word over an alphabet, it gives us back a word over the same alphabet. This is obviously computable, because to compute this, we just need the Turing machine that immediately goes into a halt state. It doesn't need to do anything. So this is computable. Very slightly more interesting is the following proposition. Which is a proposition if We have a computable function, partial function, from one alphabet to another, from words over one alphabet to another, and let's go like F. And G is a computable partial function from that second alphabet to words over the second alphabet to words over a third alphabet. Of course, all these alphabets may be the same, but they in general can differ. So if these are computable, then guess what? And what is also going to be computable? Not that hard to guess. And then so is also the composite partial function G composed with F, which is then the partial function that takes words over sigma 1 to words over sigma 3. It's almost obvious. I'm just going to, in a moment, go into one very slightly subtle point. But before doing that, the other thing I need to do is make sure that we all agree what is meant by the composition of two partial functions. Everyone knows what the composition of two total functions is. But here we've got the composition of partial functions. So that's defined by the composite of two partial functions tied to a word over the sigma 1 star alphabet. Well, what we would normally say is that this is, if it was total functions, we would say this is equal to G of F of W. But now we've got a little issue. What do we mean by G of F of W if F is undefined? Especially suppose G was the constant function that maps everything to 0. So in that case, if we apply that constant function to something that's undefined, should it be 0 or should it be the or should it be undefined? People who know a bit about programming languages, there's a kind of call by name versus call by value distinction here, or lazy versus eager distinction. The right mathematical definition for the for what the composition of two partial functions is that it equals this if f of w is defined, and if f of w is not defined, or if w is outside the domain of f, which is a partial function. So I'm using the up arrow for saying a partial thing, a partial expression is undefined. Also, even when f of w is defined, this could be undefined because g may be undefined on the value f of w. F of w need not be in the domain of definition of g. And the other thing I'm going to be a little bit careful with in this course is actually when I use equals, I'm going to only use it when both sides are defined. So we're going to, in this course, this is in the mathematical preliminaries section of the notes, but we're going to use another symbol here, known as, I shall never remember whether the tilde is on the top or the bottom. So, I seem to have done it in a different way in the notes. Oh yeah, here we go. It is on the top. So this is called Kleene equality, after Stephen Kleene, who's going to be one of the people that crops up many times in this course. So this is actually his surname is really pronounced Kleene, but people nowadays say Kleene. So that's this is called Kleene equality. And what it means is that we write this to say that two expressions that might be undefined are equal in the following sense. So this means that E is defined if and only if, E is defined if and only if E prime is defined. And if E prime is defined, sorry, if E is defined, in which case that's the same as saying if E prime is defined by the line above, then so one's defined if they both are, in which case we can talk about the values being equal. So it may seem a bit fussy, because you don't normally do this in mathematical courses. But as I say, in this course, partiality is going to play a very significant role, and so it's going to be quite important to be careful whether we're talking about defined things or values that are defined or maybe not necessarily defined. Anyway, so this is the definition of the composition. So in particular, if g were the constantly zero function, and we composed it with an f that was undefined, that gave an undefined value, then the composite would be undefined. This second line would be fine. Okay, it's not surprising that the composition of two computable functions is computable. Let's just think how we prove it. I'm not going to write down the proof, but it's a very easy proof. Well, this being computable means we have a Turing machine that computes f, and this being computable means we have another Turing machine that computes g. And all we do is, to compute the composite, we take our input word, we first run the Turing machine that computes f, then if we get to a hold state, we then run the Turing machine that computes g, and if we get to a hold state, we're done. But just to note, in order to do that, I'm making use of the slightly fussy way that I defined computing a partial function, in which I required that when we got to the hold state, we had an input word, we got the output word, and we also reset the head to the beginning of the output word. So that means that when we run the first machine, it's set the take-up in a position that we can directly run the second machine from the right start configuration. Okay. Right. So that's one small thing about computability of partial functions. And just to say, we've got the identities and we've got compositions. So with this, we have a category. For those, doesn't matter if you don't know what categories are, but for those who know about categories, we have a category in which the objects are alphabets and the morphisms are computable functions between words over the alphabets. That category is a bit poor in some ways. It doesn't have very good structure. And one of the ways of looking at what we're going to do today is we're going to improve that category. But I know most people probably don't know. You don't need to know what a category is for this course. These are just side remarks for those who do know just these things.
Maybe just one thing here. We've always been using partial functions in the sort of direct state, so some inputs may not be mapped to outputs. Do we ever benefit from looking at the partial functions as functions into set plus point, where you just map the undefined?
We could do.
Because then you just get the maybe one.
Yeah, in fact, we could do that. It actually brings in some complexities at this level to do that. But when you go to a more advanced level, it's actually the better way of doing things. But for this course, we're not going to do that. But that's a very good. Yeah, so it's a very good question. So actually, well, all right. Just to give you the story about what's going to happen today from a perspective that I'm not going to emphasize. Today, we're going to essentially define a better category than this one, although I'm not going to call it. I'm not going to call it a category. The way I'm going to define this is going to be a category of partial functions. Actually, the better definition would be to define a category of total functions, and then one can implement partiality by finding a monad on the category, which is a kind of maybe monad, but it's quite a subtle monad. So that is a nice, tidy way of doing things, but the monad is quite complicated, and at the level of this course, that's not the best way to achieve things. But you can bear that in mind, and that was a very good question. So before leaving the computability between words over alphabets, I just want to one other generalization of what we've got. So I've been talking so far today about computability of functions that take one argument. So we've just got one argument here, right? One word, so unary functions. How could we define computability for functions in several arguments? So say k arguments. So to define computability, we need to say what does it mean for a Turing machine computes. Again, for partial function in general, because the Turing machine might go into a loop. So suppose we've got a function taking k different arguments, all of which are words. So its domain is a product of the words over the alphabet sigma 1 up to sigma k, and it will return, it's again going to be a partial function, and it's going to return the word, let's just call the alphabet over which we're going to return the result sigma. So now we need to give a Turing machine k different arguments to define computability. So what would be the most convenient way to do this, given technology we've got?
Very good character don't have any alphabet and word.
Okay, so we could use a separating character. Okay, very good.
Multiple types.
Sorry?
Multiple types.
Or another way would be to use multiple text. So I'm going to use the first one now, just to, so a k-tape Turing machine, sorry, the first one, the second one. The last one, so the k-tape Turing machine computes this if for any use for any tuple of input words if we run the TM on starting configuration, where I'll just write the k-tapes like this. Okay, so here we have the first word on the first tape. I hope you can see this. The kth word on the kth tape, the head's always at the left. We're in the starting state. So if you run it on the obvious starting configuration with W1 up to WK, the machine terminates in the halt state if and only if that k tuple of words is in the domain of the partial function. So this is saying the machine is trying to give us a result if and only if we indeed have a k tuple that f applies to. And we want, in that case, that when it does halt, it gives us the right output. So it gives us f of this. So and for all W1 to WK that are in the domain of f, we have it holds in the configuration. And again, I'll just do this with a picture. So on the first tape, we require the correct output. So here we've got f of applied to W1 to WK, the word we're trying to output with. And the other k minus 1 tapes, just to tidy up nicely, you can say just it doesn't matter what's on them, but I like to tidy things up, so I'm going to require these to be blank. And we end up in the halt configuration. Oops. Not configuration, the halt state. Right, so we now have a definition of a k-argument computable partial function. But we could have used your suggestion instead with the comma, and in fact, we'll come back to that later, because a little bit at the point of it's a bit ad hoc what I've done here. I mean, yes, we're using K-tape machines, but and they're quite convenient for this exact purpose. But you know, suppose we were defining what it means for some other structure here to make it be computable rather than a product, then we wouldn't have a kind of machine tailor-made for it. So actually, what we want to do is do something more systematic in today's lecture and look at how we can define computability for functions on sets that are not words over an alphabet in general. So here we've got a product set, that's not words over an alphabet. But I'm going to give a systematic way of defining computability for functions between sets with something that allows us to use them to define computability over. And to give a very simple introduction to this, let's look at an extremely simple set that we want to define computability over, which is the set of natural numbers. And this is going to play a central role throughout the middle section of this course, what it means to compute functions over the natural numbers. Okay. So we've got what it means to compute functions between words. We're now going to look at what it means and also functions in many arguments between words. We're now going to look at functions over the natural numbers. And it's clearly not very difficult to do this. So let's just give one definition first. And having already done functions of several arguments, let's just to keep things simple, let's look at functions of one argument over the natural numbers. So I want to define computability. And I think you've probably done things like this in the exercise class already. So computability for partial functions natural numbers to natural numbers. It's a very common application area of computation, functions on natural numbers. So what's the obvious way of doing this? We know we've got Turing machines, they work on words. How do we represent numbers as words? You must have done this in the exercise classes already, and it's kind of obvious anyway. Okay, binary representation. So let's use represent numbers, or code numbers if you like, using words over what we'll call the binary alphabet. So sigma B for binary, 0, 1. They're just the symbols. And I think the easiest representation is just to say any word over this alphabet represents a number, namely the number that you get if you calculate it in binary. So we have, I'm going to write a function like this, gamma, little gamma, subscript n, for the function that given a word, a binary word, tells us what number it represents. So sigma of n of the word w is just defined to be, well, we go through the bits one by one, and we assign the appropriate weight. So to the rightmost bit, you get weight 1, and the bit next to it, you get weight 2. And the bit right on the left of the word, you get 2 to the power of the length of the word minus 1. So we go, so remember, my words, I index the symbols from the left. If the word is of length n, I go up from 0 and I count up to n minus 1 as the rightmost word, so the rightmost character. So we're going to count through indices of characters starting from the left of the word and going up to length of the word -1. And then to each bit that we get out of the word, W plus I, well, we're starting with the leftmost one. So we're going to, so the length, the total amount of weight it gets is 2 to the power of the length of the W minus I minus 1. I believe. Let me just, you're nodding, so that's reassuring. Let me just check the following in the notes, and if we've got 3 things agreeing, then that's, I do it the other way around. But it is the same. I put the, I start at the right-hand side and go that. It's okay, this is fine. I think, I do think. So good. Okay, so what do we notice this from this? We notice that all numbers have more than one representation. So for example, 3 is represented by infinitely many strings, 1, 1, 0, 1, 1. So we're allowing the leading zeros. And a 0 is represented, of course, by 0, 0, 0, 0, 0, 0. And there's another one. So what's the other word representing 0? The empty word, which we use epsilon for in notation. Okay. And then
Our natural numbers are going to be with 0.
oh yeah, our natural numbers are with 0. Yes, sorry. Is that still a controversy either at the master's level, depending which course you're in?
Mostly it's without 0, yeah.
Really? People are so what's the word? Anyway, that's better I don't say it. Okay, so M computes. Actually, let me see. Let me see what I've defined in the. Okay. So Turing machine M computes a partial function on the natural numbers if, so it's a Turing machine acting on words. So if it computes on words a function g from the Boolean alphabet, partial function g from the Boolean alphabet, the words over the Boolean alphabet. So it's mapping bit strings to bit strings, and we want it to do, we obviously want the function computed, function g of bit strings computed by the Turing machine to correctly compute the function f. That's the obvious definition. That if it computes g such that all W, so for all bit strings, if we apply, well, if we look at what G does on the word W, and we look at the number that that represents, so that's gamma n that, then this should be equal to f applied to gamma n of w. Okay, so it's f applied to the number that w represents. G computes a representation for that number. Except, yes? Yeah, except we have to be careful with this because either side here might be undefined. And we want, if one side's undefined, we want it to be undefined if and only if the other side's undefined. So that the partiality in G, that means G is only partial exactly when it's given an argument on which f is undefined. Okay, that's the only time in which G doesn't give a value. So indeed, we want clean equality there. So very good point, and that's the definition of a function on natural numbers, a Turing machine computing a function on natural numbers, and then f partial function on the natural numbers is computable if there exists a TM that computes it.
Define this, we don't need gamma n to have a section necessarily, right? Does that come into play, or do we usually assume that we can go into the other direction regardless?
Okay. That's a good question. So this function gamma n has a section, obviously, just map every number to some canonical representation, e.g. the one without leading zeros. But that hasn't played any role in the definition here. Yeah. And in fact, we could have made the definition also if we had some representation without a section, which is what we're going to do later. Although representations of the natural numbers will almost always have, I think necessarily have sections.
Some more complicated sets.
But for more complicated sets, they won't. Yeah, that's exactly the right sort of thought. So just before moving on from this, just thinking about how this is working. So f is computable if there's a Turing machine that performs the right function on representations. And I think in the exercise classes defined such functions using Turing machines, probably, to compute functions on bit strings. So we can think of G as a kind of implementation of the function f. Notice that if we fix the function f, there would be several different functions G that work as an implementation of f, because for example, the constantly zero function could be represented by the Turing machine that just always ends with just a zero on the output tape, but it could equally well be represented by the Turing machine that ends with the empty output tape. So both those will represent the constant zero function. So in general, we have many different G's that implement, if you like, the same f. On the other hand, given a G, some functions G won't implement any function because we might have a function G that takes the empty string as input onto 1 and takes the input 0 onto 0, so then it's not respecting if we have two different representations of the same number that get mapped to two different things. And it's the same number, so that's not representing any function. But if it does represent a function, it represents a unique function. Okay, and there's a bit of terminology here. We say when we've got a function G that's implementing f, we say that G realizes f. It's a realization of f. G, I'm going to use the UK spelling of realizes, S rather than Z. UK English, so G realizes f. Okay. Now we made some kind of ad hoc choices here, because rather than having the representation that we've chosen. We might not like the fact that every number has several different representations. Maybe it would simplify it if that weren't the case. In some ways it does, in some ways it makes things more complicated. So we could have an alternative representation where what we'll do is we'll say the representation of a number is the unique binary string that represents the number that has no leading zeros. Okay? So now we're going to require, we're going to call this gamma prime again. And we're going to say the domain of gamma, so now this is going to be a partial function. The domain of gamma prime again, so this is going to be those bit strings that represent a natural number according to our new representation. So how can we describe that? The set of bit strings that have no leading zeros. Okay, so
one and then all of them.
So it's all strings in the form 1W, 1 followed by W, where W is any bit string together with, as we said, the empty string. And the new representation is gamma prime is defined just on this domain and for a W in the domain. Gamma prime. Yes. And now 3 is represented just by 1, 1, and 0 is represented just by the empty string. And if we wanted 0 to be represented by 0 instead, we would just change the domain. Yeah. Okay.
Is there a reason why we aren't using the unary representation?
And what I was about to say, everyone's anticipating very well what's about, particularly you, what's about to come. What I was about to say is that we also have a very obvious third representation. Got 2 so far. The third representation we're going to now use what I call the unary alphabet. So that's words over just, don't know if I use 0 or 1 in the notes. Doesn't matter, of course, but it'd be good to be. Oh, where is it? Yeah, I use 0 in the notes. But it's kind of more intuitive with the 1 perhaps, but it doesn't really matter. And now gamma, and now this is again. So this is gamma double prime then. This is a total function from words over the unary alphabet, the numbers, and so our numbers are going to be represented by the empty word, the word 0, the word 0, 0, the word 0, 0, 0. And when we've got such a word, what number does it represent? What's your guess? The length. Yeah, the number of which is the same as the number of zeros. So the length of the word W. Okay, so we've now got 3 different ways of representing the natural numbers. For each one, we can define what it means to compute using such a representation. Maybe I'll just do that for gamma prime, because there's a slightly fiddly thing. And let me, hopefully I can so this is alternative definition. what it means for a machine to compute. If we were using the second representation, the one with no leading zeros. So actually, for that, we want G to correctly implement F. But in fact, it's not the case anymore that all words represent numbers. Only words without leading zeros represent numbers. And for G to represent F, we don't care what it does on the words that don't represent numbers. So the correct thing to put here, rather than quantifying over the whole, all words over the alphabet, the correct thing to quantify here is over the domain of the representation, namely the words without leading zeros. Okay. Of course, that's exactly what we were doing before, but because because our representation was a total function before, we didn't see that there was a distinction. And the other thing we have to do here is this statement is not enough to say that if we what's it not enough to say?
Yes, the Gauss is subjective.
Well, so all these functions are surjective. And that's going to be a general requirement, yeah. So you're anticipating what's to come. But the additional thing we need to say here is that what this does not specify, as we've said, it doesn't specify that if we have so of course we could leave this for the break till after the break. That's probably the sensible thing to do. There's something. Yeah, I think it's the necessary thing to do. I shall go to the machine and get some energy and some liquid energy. And there's a small thing we have to add to this. So I think that's a good point to start immediately after the break. So by my watch, which is a bit faster than the clock on the back wall, it's exactly 3. So we're going to start at exactly 15 minutes from now. Okay, so I don't know if it's a good thing or a bad thing, but it seems I have a natural tendency to seize up at the end of 45 minutes of lecturing anyway. So, you know, the lecturing schedule is organized in this way that we're supposed to have a break every 45 minutes. And when I'm lecturing, it seems absolutely essential that we do that. So, you know, maybe it's a good thing that I get into problems after 45 minutes of teaching. But the issue was, if we were using the second representation of the natural numbers, where we're representing a number in binary in a unique way, so we're requiring the binary representation to not have leading zeros, and we can view that representation again as a function from gamma sub n prime in this case, to distinguish it from the previous one, from words to numbers, where it's a partial function because it's now only defined on the words that are either the empty string or have leading zeros, sorry, no leading zeros, so start with a 1. So again, for G to be computing the function f, we require the same condition as before, but there's a second condition we need to impose that was automatic last time, which is again for all words in the domain of the encoding, so for all words that don't have leading zeros, what we require is that if G is defined on a word that's in the domain, so that is a representation of a number, we don't want G to map it to a word that's not a representation of a number. So we require that then So this implies that G of W belongs to the domain of gamma prime F. This could fail with just this condition, because if F is sufficiently partial, then it's possible to have, then if you give G a word that represents a number on which F is undefined, with this condition allows G to do anything with it. So adding the second condition makes sure that the partiality in F corresponds to the partiality in G from the non-termination of computation. So F applied to a number, so G is non-terminating on an input word W that represents a number if and only if F applied to the number represented by that word is non-terminating. Okay, so that's why we need this extra condition. You can think about it as a slightly subtle point. We only get this issue when we have partial representations, but this one is a partial representation. Right, so we've seen we started off with the basic idea of computability of partial functions between words over alphabets. We looked at multi-argument functions. We now looked at computing over a different kind of data, namely the natural numbers. It's obviously a very simple thing to do, to compute over the natural numbers using strings, but we saw that using words, we saw that there are various different natural definitions one could give. It's not surprising that they're all equivalent. What I want to do for the main content of the lecture is introduce some systematic machinery for looking at this. So looking at different kinds of representations and talking about them being equivalent to each other and having a notion of computability between representations. So let me move the camera. The idea, so now, for particularly this hour of the lecture and to an extent for the whole of today, we're going to be quite abstract. And then next week we'll get back to being more concrete. Yeah. Yes?
Yes, I wanted to ask about this. Yeah, about this. Excuse me if I didn't understand the explanation correctly, but could we just circumvent, so drop the second condition by just writing gamma there? Because gamma without the
Gamma where?
yeah, gamma without the yes. Not right, yes.
But I'm trying to express what it means for a function on natural numbers to be computable with respect to the second representation, the gamma prime representation. So we shouldn't use gamma at all. This is supposed to be a definition of computability. So this is computability relative to the representation gamma prime. The one that doesn't have leading
example of representation.
So this is using a specific example of a representation. Yes.
Yeah. So what seems to me is that such a definition, while not traditional, would work. If we said, yeah, we can use the gamma without the not prime, so without the thick, yeah, because like
Well, that would be a very peculiar definition because you'd be requiring something. You'd be requiring your function G to have some property that's much stronger than just the property needed for the gamma prime representation. The gamma prime representation, we're using only words that don't have leading zeros. We don't want to require, I mean, here we've got this quantification, we're only looking at words in the domain of gamma prime. I mean, it seems very unnatural to start mixing representations in here. So anyway, let's carry on and we can discuss this more in the break, appropriate. So the basic idea now is we want to have a notion. So we aim for computability, notion of computability for partial functions, because partiality is natural, from A to B, where A and B are arbitrary sets. They could be natural numbers, it could be product sets, which will allow us to talk about multi-argument functions. They could also be other interesting sets. So a particularly useful one for later in the course, which we're going to do in the exercise class next week, is going to be the set of dyadic rational numbers, for example, and as something that it's nice to compute with. But obviously they can't be arbitrary sets. I mean, for those of you who know some set theory, arbitrary sets can be very large and complicated. So they need to be arbitrary sets that are suitable for computing with. And how do we say they're suitable for computing? Well, they're suitable for computing if we have a way of representing the sets as words over an alphabet. So our sets together that have representations. By representation, I mean representation of its elements using words over an alphabet. So that leads us to the main definition today. This is a definition. Representation of a set. Let me just. So I just want to be notationally consistent with the notes because I know. Start writing letters, it might get confusing. Okay, so X by words over an alphabet sigma. So alphabets are always assumed to be finite sets of symbols. It's simply a partial sorry, it's okay to say partial surjective function, but for some reason the adjectives are better in the other order. I don't know what the really underlying reason is, but there's always this funny thing in English that adjectives tend to go in some sort of natural order. So anyway, it's a surjective partial function gamma from words over sigma. So now I'm going to start using, there's I don't know if people have seen this before, but in mathematics one sometimes uses a double arrow to emphasize that you're looking at surjective functions. So because it's surjective partial function, we're going to use a partial double arrow here. I'm not sure that one finds this symbol in many places in mathematics. So the symbol I use in the LaTeX notes is a hack of two overlaid partial arrow symbols on top of each other. But anyway, I like it. So anyway, it's just that. And we see so subjectivity says every element of the set has to be represented by at least one word, but perhaps several. And the partiality, that's important because we don't require that we don't require that every word needs to be the representation of an element of fact. For example, in the case of the representation of numbers without leaving zeros, we didn't have every word. We only had some words being representations of numbers. So we have already seen, three different representations natural numbers, namely gamma sub n, gamma prime sub n, and gamma double prime sub n. And there are lots of other representations of the numbers, that the one we use in everyday life is something rather similar to gamma sub n, but where we use the decimal alphabet rather than the binary alphabet. Anyway, we've got three examples of representations of numbers. But the notion of representation makes sense for any set X. However, because it's got to be surjective, so as I said last week, it's not important in this course it's not very important to know about cardinality of sets for those of you who did logic and logics in the first year, and the other courses on sets, you will know about the notion of cardinality of a set. But for those who know about it, what is the cardinality of the set of words over a finite alphabet?
It's countable.
It's countable. So if you've got a surjective, there's a count of the infinite, it's always a count of the infinite set for a non-empty alphabet. So we've got a surjection from a countable set to set X. We can only represent countable sets. Okay, so only countable sets can have representations.
Is it sufficient here to get a section without choice or multiple sets? Because I'm just thinking somewhat if because with this notion we're not going to be able to talk, for example, about computable real number.
Yeah, so indeed. So we're going to use another notion for computable real number later in the course. Yes. Very good.
So what I mean also is that I mean, is it still going to, are we still going to need somewhere the fact that we don't necessarily have a section, so we just want to do.
Right. So I wouldn't worry too much about some. So for those who don't know what sections are, this discussion doesn't matter very much. But for those who do know what sections are, so it's a mathematical question: does this function have a section? And in general, the assertion that all surjective functions have sections is equivalent to the axiom of choice. In this case, because it's a countable set here, mathematically there always exists a surjection, and there always exists a section with it, without choice, without any choice at all. There's always a mathematical section, but it doesn't play. It's not important for us to have a section in that sense, even though it exists. Okay, so that's the notion of a representation. So we've got three representations of the numbers. Of course, to go to representations of arbitrary sets, it would be interesting to see representations of some other sets other than just the numbers. I'm going to leave most of that to the exercise class next week. Okay, so just wait till then, although we'll see one other important example of representation in the third part of the lecture. Of a concrete representation in the third part of the lecture. So what does the notion of representation give us? Allows us to define the notion of computable partial function between the represented sets. And actually, although I rubbed it off, it's going to be very similar to what I just had here. But I rubbed it off because I realized if I was going to change that, it was going to end up looking very messy. So I'll try that it doesn't quite look so messy. So given represented sets, or let's just say representations. And again, I just want to be consistent notationally with the notes. Okay, so I'm using x1 and x2. So we've got two represented sets, x1. So that's represented by words over an alphabet sigma 1, and a partial surjective function from that first alphabet onto x1, and gamma 2 is another representation, so that the representation of the set x2 by, so again, a partial surjective function from over the alphabet sigma 2, a function, a partial function f from x1 to x2. So the nice thing is we can talk about the computability of partial functions between arbitrary sets, as long as those sets come with given representations. So it is computable Now, when we say computable, of course, the sets might have other it's not the case that there's only one representation possible for any given set. We've already seen 3 different representations for the natural numbers. So the notion of computability is really relative to the representation. So I'm going to say it's gamma 1 arrow gamma 2 computable. So representable is a function from the representation gamma 1 to the representation gamma 2. But in practice, we're often going to omit this gamma 1 to gamma 2 because we'll soon get to the situation that when we talk about a set, we have our favorite representation of the set, and we're just talking about that favorite representation. And I should say, in the case of the natural numbers, our favorite representation is the first one, the one that does allow leading zeros. And the reason for that is that if you write Turing machine programs on natural numbers, it tends to be easiest to write them for this representation. If you use this one, you have to do a lot of cleaning. You have to do some cleaning up afterwards to get rid of leading zeros and this sort of thing. I mean, it's a minor decision, really, but it tends to be like that. So, right, so it's computable if, so just as before, what we need is a computable partial function on words, so one that's just computed by the Turing machine in the way we discussed at the beginning of the lecture. So if there exists a computable partial function P from words over the first alphabet to words over the second alphabet, such that it does the right thing for words representing elements of x1. It maps words representing elements of x1 to words representing elements of x2 in such a way that it's correctly implementing the function f. Such that so again, we only require it to be well behaved on words that represent elements of x1. So we look, so we only require it to behave well on words in the domain of sigma 1. And for such words, we require 2 properties to hold. So the first property is again that if G of W is defined, then G of W, so whenever G is defined on a word representing an element of x1, the value of G of W is a word representing an element of x2. So then G of W belongs to the domain of gamma 2. And the second condition is that condition we had before, that if we compute G of W, then if it's defined, it's going to give us something, it's going to give us a representation of an element of x2. We can get that representation, we can get that element of x2 by applying the representation function. And that should be the same thing as applying f to the element of x1 that we got from the word. I'm sorry, and once again, this is a clean equality because both sides may be undefined here. One needs to be defined if and only if the other is. Okay, so these are in the notes. For some reason in the notes, and I didn't have that much editing. I did make some changes this year, but I didn't have that much editing time, so I didn't change this. For some reason, I put them in the other order last year, but to my mind, actually, this is the more natural order what I've put in here. So anyway, so I called these little 1 and little 2, and these are the two conditions. So basically, now let's just familiar because it's the same thing we saw for the natural numbers representation. And just to say, one can view this as a diagram, which is, and I'm actually going to give a different diagram from the one in the notes, but it's equivalent. Well, it's equivalent. It's equivalent. What I'm going to give is equivalent to these two properties. So equivalently, we have property 2. And what does property 2 say? Well, property 2 says if we consider the domain of gamma 1, and we look at G is a partial function that maps the domain of gamma 1 to the domain of gamma 2. That's what property 2 is saying. It's saying that if G is defined on something in the domain of gamma 1, it falls into the domain of gamma 2. So G gives us a partial function in the domain of gamma 1 to the domain of gamma 2. Then we've got our two partial surjective functions here with representations gamma 1 and gamma 2. We've got the set x1 and the set x2, and the partial function f. So what we're requiring is property 2 here, which allows us to write this G in here, together with the requirement that this diagram commutes, for those who know what commuting diagram means. For those who don't, it means that the composite functions here are equal to the composite functions here. Okay, so this commutes. That's an alternative way of looking at it. If we find that abstract, then this definition is all you really need. So this is the important definition here. Once again, it's saying that G is a computation on words that implements the function f. And again, we're going to use this terminology. When these conditions hold, we say G realizes f. Okay. But it's very easy from the definition to verify that if we have just wondering where to write it. So we have representations gamma 1 the next one, so we're going to have three representations, gamma 2, x2, and gamma 3 from sigma 3 to x3. We've got three represented sets. Then if we've got that f from x1 to x2 is gamma 1 to gamma 2 computable, so computable according to these two representations, and g from x2 to x3 is gamma 2 to gamma 3 computable. Then opposite function g from f from x1 to x3, opposite partial function as defined at the beginning of the lecture is, what am I going to say here?
Gamma 1 to gamma 3.
So it's gamma 1 to gamma 3 computable. So computable partial functions between represented sets compose. Of course, the identity function is computable on any represented set. So we now have another category whose objects, for those, so once again, this remark is just for those who know what categories are and is not important if you don't know what categories are, but I like to make side comments that to provide some external perspective for those who are open to it. So we have another category whose objects are represented sets or are representations, and whose morphisms are computable partial functions between representations. That's quite a nice category. But actually, the really nice category is the one that's even a little bit simpler to define, where you restrict to the total functions that are computable. And that category is exactly the category of what are called modest sets in the realizability world. And this is the, well, there's a slight issue that we're using strings for words for representations rather than natural numbers, but it's basically what's called the category of modest sets in the world of realizability. And that's a really nice category. It has lots of good category theoretic structure. It's Cartesian closed, for example. It's even locally Cartesian closed. Anyway, so, and the partial category can be recovered using a suitable monad. Right, that's enough remarks on the category. So this is a proposition that the computable partial functions compose. There's a bit of a fiddly proof of that in the lecture notes, and the fiddly, the intricacy in the proof is just to do with having to be very careful about when things are defined and making sure all the conditions about if something's defined and something else is defined and so on, that those all work out. So it's a sort of boring result that requires only that has a slightly fiddly proof just because partiality is a little bit of a subtle notion. So for those of you who like an exercise in careful thinking, which is basically all it is, I suggest you try to prove this for yourself. But it really is, it doesn't require any deep insights, it really is just an exercise in careful thinking. I should say that actually this way of looking at it makes it almost obvious that things compose, because then it's just pasting two squares next to each other and you just have to verify the two condition. Anyway, good. So, right. So we've got now a notion of computability between arbitrary represented sets. So we could define, we can look again at the case of the natural numbers. How do we? That's our main example so far. So let's just think what we could do for the natural numbers. So we have actually various choices for how we define computability for partial functions between the natural numbers. Choices for defining computability of partial functions. Natural numbers. So the one we took as our definition, we can now rephrase as using our canonical representation. We had the representation gamma n, so we could take gamma n arrows gamma n computable. Or we could use the second definition, one that doesn't allow leading zeros. Or we could take the third definition, the unary one, just sequences of zeros. Or if we wanted, we could even mix them. So we could use one representation like the canonical one, allowing leading zeros for the domain, but require that we clean up the answer and don't have leading zeros at the end. Again, I'm not going to write out, or we could bring in another representation like the decimal one or something else. So we've got plenty of options. So which is the right notion of computability for functions of the natural numbers? Well, guess what the situation is? They're all equivalent. So these all go inside. It doesn't matter, we have to choose some representation to make a definition, but in the end, it doesn't matter which one you choose, the definitions turn out to all be equivalent. And why is that? Well, they coincide for a reason, and you don't need to think about the functions. The equivalence of the part of the notion of computability of functions is going to be a consequence of a simpler property, which is the representations themselves are equivalent. So we're going to have a notion of what it means for two representations to be equivalent, and all these representations are equivalent to each other. And that means that they define the same notion of computability. So this is because the representations three representations were given, but any other reasonable representation that you could dream up are equivalent. Okay, so what does it mean for two representations to be equivalent to each other? And this is rather nice little concept. Once again, I'll just check the notes just to see what notation I use. Right. The point about equivalence is we're going to have a notion what it means for two representations of the same set to be equivalent. So here that makes sense because all it makes sense to talk about equivalence because all representations were representations of the natural numbers. But in general, if you've got two representations of the same set, you can say, are these two representations equivalent? So this is an important definition. So it requires a good pen. Two representations. Gamma 1, say, from an alphabet sigma 1 words over an alphabet sigma 1 to a set X, and gamma 2, so representations might be from a different alphabet, but the point is it needs to be a representation of the same set X, but the same set. Emphasize that they're said to be are equivalent if, just wondering, can anyone guess what this definition is going to be? Yes, okay, but that's, we can say that in a simple way. So, okay, yeah.
We have to have the identity function.
Right, very good. In both directions.
Yeah.
Yeah, exactly.
Yeah.
So if the identity function, this is the total function on the set X. Of course, this goes only in one direction, but it's going from the set to itself. But it needs to be computable in both directions, in the sense both computable from sigma 1 to sigma 2 and from sigma 2 to sigma 1. So it's both sigma 1 arrows sigma 2 and so gamma, I keep on saying, no, sorry, sigma is the alphabet, gamma 1 arrows gamma 2 and gamma 2 arrows gamma 1. The sigma is the capital and the gamma is the little one. And I don't know, I've been writing small gammas like this for ages. I don't dare to look to see how you want to actually write them. We've got a feeling it's probably completely wrong. Okay, so it's simply that. A little puzzle. So I said 2 blackboards ago, when I was writing on this board before, I said I didn't write it down when we were talking about composition. I said the identity function is always computable, of course. So now we're asking as a requirement the identity function to be computable. So maybe that's a bit puzzling. But the first time I meant the identity function is always computable from a representation to itself. Okay. But if you mix the representation, then you've got some work to do. So, for example, let's see that our first our favorite representation of the natural numbers is equivalent to the unary representation of the natural numbers. So, for example, our favorite representation allowing leading zeros in binary and the unary representation, gamma double prime n, are computable. And guess what? I didn't actually prepare this bit before the lecture, and I only just decided to do it. And it's and we're getting to that point that my brain naturally seizes up. So we shall see whether I'm able to read this or not. But if not, we're going to have a break, and I shall hopefully be able to do it after the break. But should not be difficult. So we want to show that the identity function mapping a number to itself is both. Sorry, I'm writing a sigma now. So it's computable from the canonical representation allowing leading zeros to the unary representation.
The representation are probably equivalent.
Oh yeah, are equivalent. Thank you very much. Yes. Yeah, you see, it's getting to that time that break is needed. Right, and the other way around, gamma double prime n to gamma n computable. Okay, so what do we do for this? Well, so what do we need here? In this case, we need a Turing machine. We write a Turing machine that takes a binary word and needs to convert it to the right unary word representing the same number. So you simply So this says a bit, let's say build a Turing machine that reads a W in over the binary alphabet and computes and outputs. Well, it has to output a string of zeros. And how many zeros does it need to output? Well, it needs to output exactly as many zeros as this binary word for the number that this binary word represents, which is gamma of n of W. So basically, we need to write a Turing machine that reads a binary number, understands how long it is, and outputs exactly that many zeros. So I'm not going to actually write the Turing machine, but you can hopefully see for yourselves that that's not a particularly difficult process to compute. You can do that. So as long as that's a good way of doing it. So as long as you can subtract one, which you probably did in the exercise classes, or anyways, as long as you can subtract one, that's decrement to a binary number. You work with two takes, say, decrement the number, and each time you decrement, adding on the zero to the output taken as soon as you get to zero. As soon as you get to zero on the binary number. Okay, so that's a good way. I think the other one could. And the other one is build a TM that reads a U, let's say, over the unary alphabet and converts to binary. There is something in the real world, there'll be something very nasty about particularly this first Turing machine. What is it? Why would we never do this in practice? And why would we never use the unary notation in practice? It's exponential. Yeah, because it's not efficient for the binary representation we need to represent a number n. We need order of logarithm, binary logarithm of logarithm base 2 of the n number of bits. Whereas the unary representation is exponential in that number of bits, and so this is an exponential time algorithm. But for the purposes of computability, there's no problem. We're not worried about time. Just things have to terminate eventually, and we perfectly well do have algorithms that terminate these two things. Okay, so it's now 1 minute. So now it's exactly 4 o'clock by the clock on the back wall. So we can use the clock on the back wall, and we'll start at 4:15 by the clock on the back wall. Okay, questions? Right, good.
Any question that's actually connected to what?
Okay, so we're now being recorded, so yeah, so question.
We looked at the two equivalents of these two gamma functions.
Yeah.
Like we could define them in the sense that the actual thing that passed, that computed the identity, the thing, like the two functions, if for example we did decrement and just add a number 0, or on the other hand, increment, these were actually inverses in some sense.
Yes.
Is this like the fact that these two act in a properly inverse way meaningful?
So the point is when we should prove those two equivalences were so those two representations were equivalent. We had two implementations, a G in one direction and a G in the other direction. And you start with the unary representation, you go around the loop, that's the identity. Whereas if you go the other way around, it's not the identity. Because you'll be you're losing the distinction between these lots of but but essentially whatever you've got, I mean the point is you always have a G in one direction and a different G in the other direction that are computing inverses between the represented sets in a sense. Anyway, so one thing, we've got this very powerful framework. It's very powerful because we can represent arbitrary countable sets in many different ways, and when we have the notion of representation, we can actually do quite a lot of things with representations. as we'll see in a moment, something we can do. But for the purposes we've seen so far, we've basically been talking about representations of the natural numbers. And considering the general notion of representation to talk about computability on the natural numbers is really overkill. It's like introducing some quite abstract framework to talk about something that's very, very simple in the computation with the natural numbers. But we start to get back some payoff or some payback from having such an abstract notion when we start thinking about now we've got this notion of representation, perhaps we can perform constructions on representations like constructions on sets. I'm just going to give one example, but it's a very useful example of that, and that's constructing a product representation, like the construction of a product set, if you're given some number of representations. So we're at the master's level here, so we might as well just do K argument products straight off rather than starting with binary products. So given representations of potentially K different sets, what's important is we have K representations. They could all be the same if you want, but we're going to have gamma 1 is a representation of x1 all the way up to gamma k, the representation, so a surjective partial function from some appropriate words over some appropriate alphabet sigma k to the set sigma k. We're going to construct a canonical representation of the product set of x1 times x2 times up to xk. So the set of ordered k tuples of elements from x1 to xk. So we construct a product representation try and get a better pen for this. So I'm going to call the representation gamma. We're going to use another alphabet for gamma, so it's going to be sigma. And as I said, this is going to be a representation, so it's a surjective partial function from words over sigma to the product set x1 times the product, k-fold product of those k sets. Product of those k sets. Okay, so to explain this, I need to say what sigma is, and define what this partial function gamma is. So where sigma is defined to be, and now we come back to when I talked about computing functions in many arguments, we had the two ways of doing it. I did the Turing machine way before, but the other suggestion at the start was to implement k tuples by adding to the alphabet some separating symbol like a comma to separate out different inputs. And that's exactly how we're going to represent the set of k tuples. So the suggestion in the first arrow, the person who did it is distracted, but anyway, your suggestion, never mind, was a good one. So the suggestion, so to get an alphabet for the k tuples, yes, your suggestion. Yeah, hi. Yeah, so your suggestion in the first hour, we're now going to use it to represent k tuples. So we take these. So we're going to take the union of all the alphabets we got, and we'll disjoint union that with a new symbol, which we'll call comma, which is our separator. Okay, so this means disjoint union. And then the domain of, so gamma's a partial function is going to be defined on those words. So we're going to define it by specifying its domain and then giving it an action by how it behaves. So its domain is going to be simply those words of the form W1, comma, W2, comma, dot, 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 WK, where W1 is a word over sigma 1 star. Oh, no, so W1, so this isn't correct. What should it be? Fine. W1 needs to be in the domain of gamma 1. W2 in the domain of gamma 2. So on, WK in the domain gamma K. So representation of a K tuple is a K tuple of words, each representing something in the represented set x1 to xk. And then simply gamma applied to something in its domain, which always has this form, is of course defined to be the K tuple in the product set, which is the element of x1 of the set x1 that W1 represents. So we can get that by applying gamma 1 to it, and all the way down to the element of the set x, the set capital XK that the word WK represents. Okay, and that's the definition of product representation. So a very simple definition using the idea that we already had in the first paragraph. That's the remote. And we'll write. We have a standard notation for this. So standard notation. I'm going to, rather than writing gamma, I'm going to write gamma 1 times gamma k for the product representation. And I'll call the alphabet sigma of gamma 1 times gamma k. Okay. So the product representation is this is exactly this sigma. It's a subjective partial function of the product x1. And just to make more remarks for those who know something about categories. So we were previously considering a category whose objects are representations and whose morphisms are either partial computable functions or computable partial functions, or the answer between the representations, or this, as I said, a nicer alternative, which is to consider computable total functions for the category. So a smaller category consists of total functions. In the category of total functions, this product gives us a category theoretic product. So a product in the usual category theoretic sense. It's not a product in the partial category, but it's a product.
But then you have projections, so
yeah, so we have the projections are in the total category, so they're also there in the partial category because all total maps are partial, but the universal property fails. And the projections are not natural by category. So they're not natural, they're not components of a natural transformation. I think, as I recall, I haven't thought about this for a long time. Okay, and once we've got the representation of products, we can use this to define computability of partial functions in k arguments, just like we were doing for the natural numbers earlier. And we could do this for k arguments from k represented sets to another represented set. I'm not going to bother writing that out. You can kind of think up the definition for yourself. It's not really important. I'm just going to instantiate it and it's not important to cover it today. I'm just going to instantiate it once again in the case of the natural numbers. So we're now going to get the second definition of what it means for a partial functioning k arguments on the natural numbers to be computable. But this is our official definition. We had the definition earlier using multi-tape Turing machines, but we're now going to have the official definition for this course of what it means for partial functioning k arguments on the natural numbers to be computable. So a function, partial function, okay, f from, so it's now a function in k arguments on the natural numbers. So it's the main, so the, oh, sorry, it's not surjective. So a partial function from k tuples of natural numbers to natural numbers is said to be computable. Definition, if it is computable as a partial function from the product representation to the representation of the natural numbers, where we take our canonical gamma sub n for the representation of the natural numbers. But because all the representations of the natural numbers are equivalent, it doesn't actually matter which one we take, but we'll just use the canonical one because we prefer it. So if it is gamma, so the gamma sub n times gamma sub n to gamma sub n, computable. The represent computable from the product representation to the canonical representation of the natural numbers. Now, of course, we require this to be the k-fold product. Okay. So that's our official definition of computable partial function. And it's no surprise, I'm sure, by now to know that we had a definition at the beginning of the lecture using multi-tape Turing machines. I hope nobody is surprised that this is equivalent. So this is equivalent to the earlier definition using multi-tape Turing machines. And if you want to, you can think about why these are equivalent. So, on the one hand, you have a single tape Turing machine that takes an input word from this product representation, and you have to convert that to a multi-tape Turing machine that's going to take its inputs on k different tapes. And in the other direction, you start off with the multi-tape Turing machine that takes the inputs on k different tapes. You have to convert that to a machine that works. Doesn't matter if it's single tape or not, because we can reduce multi-tape machines to single tape machines, but it converts it to a machine that takes the input as the K2. Okay. Good. So we've got product representations. So we're here a little bit using the abstract framework. We've got the here we're representing a product set, so it's an example of representing. We're representing now more interesting sets than the natural numbers. We're representing products of natural numbers, but also products of natural numbers. Which, the product of a product is just a product. But anyway, we can see some of the power of the framework. Yes, Kevin.
General representation invariance functions over natural still requires some proof, right?
Okay, so there's the representation invariance that we showed that if you have k, when you define the product, well, it's good that the camera's gone to this board. If we've got k representations and we start off with k different representations that are equivalent to the first k, then the product of the first k representations is equivalent to the product of the second k representations. That gives you a way of bootstrapping the equivalence property. That may be mentioned in the notes. I'm not sure, but anyway, that's true, and you can think about it. We don't want to cover everything in detail, but yes, good point. Does that answer the question? Yeah, okay. Right, so I want to do one final thing today. So we've been looking at the notion of computable function today, partial function. But of course, we have the other thing we're doing with computability, the other main thing we've been doing, which was deciding and semi-deciding languages. So is there an analog for sets? So languages are sets of words. Is there an analog of? So when we've got representations of arbitrary sets, we have a notion of computable function. Do we also have an analog to the notion of decidable and semi-decidable? And we do, and these turn out to be properties of, we want to talk about whether a subset of the represented set is decidable or semi-decidable. So given a representation, a represented set, so let's call it gamma with alphabet sigma, and we're representing the set X. A subset A of X is decidable if, well, so to decide a language, we needed a Turing machine that inputs a word and then either goes into an accept state if the word's in the language, or a reject state if the word's not in the language. So what we're going to require here is that we input essentially an element of X, and we need to go into an accept state if that's an element of A, and a reject state if not. But of course, we can't actually input an element of X, but what we can input is an element as a word representing an element of X. So what we require is if there exists a Turing machine that for any word that represents an element of X, and it's important we quantify over all words in X here, and we're going to decide whether or not they belong to A or not. So that for all or such that, let's say, so for all words representing elements of X, that's for all words in the domain of the representation. If the element represented by W belongs to A, the TM accepts, so halts in the accept state when given W as input, so it accepts input W. And if the input word does not belong to A, the TM rejects, so halts in the reject state on W. Okay, that's decidable. And we could again actually define this in two stages, like I did earlier. We could say what it means for a Turing machine to decide A, and then a set is decidable if and only if there exists a Turing machine that decides the set A. But I've just wrapped the two things up in one, but you can easily extract for this what it means for a Turing machine to decide A. Yes, question somewhere?
Yes. Under this definition, isn't it possible that this desired Turing machine just accepts garbage? So something that isn't even in the domain.
Yeah, so the Turing machine is allowed to do whatever it wants on elements not in the domain. Yeah, so it can accept garbage, but we're only interested in words that we're always only interested in words that represent elements of X. For those words, the Turing machine needs to be able to make a computational decision between accepting and rejecting. Okay, and that's actually really important in more advanced computability theory, that one allows the Turing machine to do garbage on the outside. We're not going to actually see examples of that, but it is actually a crucial feature. It would be a bad definition if you tried to get the Turing machine to do something constrained on words that don't represent elements of X. You'd end up with a bad definition. And semi-decidable. So this should be routine by now on the course, but anyway, let's write it out. So this is if there exists Tm such that for all W for every word that represents an element of X. Now, it's not enough to just put the first line here, because we also need to require that if something is not in A, then we don't require it to be rejected, because that would be too strong for semi-decidability, but we still require that it's not accepted. So we require that Tm accepts W if and only if, IFF, if and only if gamma of W belongs to the set A. So for words outside, for words that represent elements of X that are outside the set A, the Turing machine may go into a loop. It may do something arbitrary, it may even reject, but it must not accept a word that's outside A. Okay? And what I want to end with is a characterization of these two properties in terms of computable functions. So here we're looking at, we've kind of brought Turing machines into the picture again. And now that we've got this abstract notion of represented set and computable function between them, it's a little bit unfortunate if we still need to make definitions by using Turing machines. And actually we don't need to, because what I'm going to end with is showing that there's a way of coding up these same properties entirely using the notion of computability of functions between represented sets, rather than thinking about Turing machines. Although, some people might find it easier to think about Turing machines. So let's go to the other board and so I'm going to do some very simple mathematics now, because it's we've been going for nearly 2.5 hours, so time we should do something very simple. So we remember, for a subset A in X, we have a characteristic function, also sometimes called an indicator function. And just to remind myself what notation I use for this in the notes. Okay. I use Z rather than A, but it doesn't matter. So chi sub A, which goes from X to the set 0, 1. And, this is like elementary set theory stuff, but the characteristic function of a set is simply that function that takes, so chi of A of equal X is 1 if X belongs to A, and 0 if X does not belong to A. So everybody knows this, right? And I don't know if you're all used to notation chi, but anyway, so sometimes one uses like 1 sub A, the indicator function, and things like that. But anyway. So just a little warning here, Devil in the teaching assistant really loves to use 0 for true and 1 for false. So he loves it so much that he will probably insist on doing that in exercise classes, I'm not sure. But anyway, it's easy to switch one's head around. Anyway, we have the notion of a characteristic function. But in this course, partial functions are very important. So we're also going to look at the partial characteristic function. I'm calling this, right, in the notes, I call this set kind of blackboard bold B for the set of Booleans, or bits. Fortunately, everything starts with all the right words start with B, so it's nice, easy to choose the letter. So the partial characteristic function, I'm going to put a P in the superscript position here, and that, well, there's no particular reason to use B here because we're only going to need one value. But anyway, just to make the things the same, I'm going to use B. So the partial characteristic function is defined to be 1 if x belongs to A, then instead of returning a value when x doesn't belong to A, it's undefined. So x does not belong to A. What do I need to put here? Squiggly equality, clean equality, yes. So this is because this may be undefined. Whereas this one's always defined, this is not. And the proposition is given a representation set, so again gamma from some alphabet, so representing some set x, and a subset A, subset of x, and firstly, A is, let's say, is gamma decidable. Sorry, I should have said when I defined the notion of decidable, we should really say gamma decidable and gamma semi-decidable here, because it's relative to the. It depends on the representation, but in practice, as I said, one always basically has a representation in mind, so we tend not to make these representations very explicit when we talk about things. For example, when we talk about the natural numbers, we've chosen our representation of the natural numbers, we know which representation we're talking about. We've chosen a representation that's binary and allows me to do it. Anyway, the proposition says A is gamma decidable if and only if its characteristic function I sub A from x to 0, 1 is computable. So we've got the representation gamma for x, and it's going to be computable relative to the canonical representation of the Booleans, which I have yet to define. And the second statement says that A is gamma semi-decidable if and only if its partial characteristic function chi p A from x to 0 to Booleans 0, 1 is again gamma. What's the representation of the Booleans? Well, you can choose your own favorite one, but the most obvious one is gamma. The representation of the Booleans uses the Boolean alphabet, sigma B, So the alphabet that consists of zeros and ones, and is a partial total function going to the set Z, which is the set 0, 1.
A total function to be computable, we just take it as a partial function.
Yes, sorry, so for a total function to be computable, it's just the same definition of computable we had before, because the representations can still be partial. And the G can also be partial, even for a total function. It just needs to be total on the domain of gamma 1. Yeah, so that's a good point, yeah. Anyway, so this representation, you can choose almost anything, but I'm going to do the one that the domain of the representation of the Boolean. So here we've got arbitrary words over the Boolean alphabet, over the binary alphabet. Of course, the most natural thing to do is simply to take the single character word 0 and 1, and then gamma b of maps 0 to 0 and 1 to 1. Okay, so you simply represent Booleans as the single character. It's the single character bits, which is the most natural thing to do. So we have this proposition that being decidable or semi-decidable, defined with Turing machines that in the first case accept and reject, and in the second case accept in the right cases, but the only requirement in the other cases is that they don't accept. But these definitions are equivalent to the computability of in one case characteristic functions, in the other case partial characteristic functions. So there's a proof of the equivalence of one here in the lecture notes. All I want to say in the lecture is, it's not really difficult, because what you have, on the one hand, you have a Turing machine that outputs a 0 or a 1, ends up outputting a 0 or a 1 on the output tape, and you want to change it to a Turing machine that accepts and rejects, then you simply wait till you output 0, would output 0 or 1, and if you were outputting 1, you'd go into accept. If you're outputting 0, you would go into reject. In the other direction, you've got a Turing machine that accepts and rejects. You just, instead of accepting, you output a 0, output a 1, and instead of rejecting, you output a 0. And here you do a similar thing. It accepts thing. So it's actually, I didn't have a chance to edit the proof in the notes, but it's several lines long. It doesn't need to be, because it's an absolutely trivial proposition. So you can take this in two ways, this proposition. Either we can keep the Turing machine definition as the definition and have this equivalence. Then in any case, in the future, we're going to basically work with this version, not with the Turing machine version. Or we can just say, hey, what the hell about the Turing machines? And we understand the computability of functions between represented sets. Let's just work with this definition. Good. Well, that's everything today. So we're ending a bit early. Are there any questions? Good. Right. So, see you next week.